Hello friends, good evening. How are you all? Hello friends, good evening. My name is Sarita. I am UGC net qualified. I did MTech and I did MCA. Okay friends, yesterday we already discussed some important topics from DBMS. Yesterday we saw what is first normalization, what is first normal form and what is second normal form, third normal form. Okay, we will do some quick revision of normalization. Initially, initially any the given data will be in unnormalized form, right? What is first normalization? Single value in single cell. In a relation, we have to maintain a single value in a single cell. Value of each column belongs to same domain, and primary key can determine all the attributes of the given relation. And what is second normal form? Second normal form is fully functional dependent on candidate key. That means first condition is it should fully functional dependent on candidate key. Okay, if what is second rule? If left hand side is not candidate key, the right hand side should be prime. Okay, what the third rule in the second normal form is non-prime to non-prime is also allowed in second normal form. But in second normal form, partial dependency is not allowed. What is partial dependency also? Yesterday we have discussed very clearly. If you have not watched yesterday lesson, please watch that. Then you will get clear idea what is partial dependency. Partial dependency means prime to non-prime. Prime to non-prime. This is called partial dependency. Okay. That means a non-prime attribute should be fully functional dependent on candidate key. It should not be prime attribute. What is prime also we have discussed. Prime means it is a part of candidate key. Part of candidate key is called prime. Okay, I hope you are cleared with this second normal form. What is third normal form? Every every second normal form is in third normal form. We have here, please see this diagram. If a relation is in BCNF means it will be in 3NF, 2NF and 1NF also. If a relation is in 3NF, it will be in 2NF and 1NF. If a relation is in 2NF, it will be in 3NF and BCNF. No, I think this is, if a relation is in 1NF, then it will be in 2NF. If a relation is in 2NF, then it will be in 3NF. No, which is right? Sorry, I will see. Okay, yes. If a relation is in BCNF, that means it will be in 3NF, right? If it is in 3NF, it will be in 1NF. If a relation is in 2NF, it will be in first normal form. Okay friends, this is the diagram you have to remember. Okay, next, third normal form. What is third normal form? Full for each functional dependency, LHS must be candidate key or super key. LHS is must be candidate key or super key. Okay. If it is not like that, then RHS should be prime. Any of these two should be true for the third normal form. Okay, what is Boy's chord normal form or BCNF? BCNF LHS should be super key or candidate key. Okay, right hand side prime condition is not allowed in BCNF. If right hand side prime also, it is not in BCNF. For third normal form, if right hand side is prime, then it is in 3NF. If suppose left hand side is not candidate key or super key, then right hand side is prime, there is no problem. We can say that that relation is in third normal form. Okay friends, I hope you are clear with the normalization concept. Now we will do some questions. How to find the candidate key, how to find the whether the given relation is there in which normal form. We will see the some examples. Okay, this is the GATE 2013 question. Here in this question, two questions are given. First question is, how many candidate keys does the relation R have? We have to find the number of candidate keys. How many means here the answer is given 3, 4, 5, 6. We have to find how many. Next, the second question is, we have to find is the given relation is there in which normal form. 1NF but not in 2NF, in 2NF but not in 3NF, in 3NF but not in BCNF. We have to see which normal form is the given relation. For that, first we have to find the candidate keys, right? To say the relation is in 2NF, 1NF or anything, first of all we have to know what are the candidate keys. From the candidate keys only we came to know what are prime attributes and what are non-prime attributes. First of all, we will write the given functional dependencies of this relation are A, B, C, D, E, F, G, H. The given functional dependencies are CH to G, A to BC, and B to CFH, E to A, F to EG. These are the given functional dependencies. Okay, before finding the candidate keys or primary keys, first of all, we have to see the right hand side of the given functional dependencies. Is all the attributes present in right hand side from the given relation? We will see A is there, A, B, C, D is not present, right? D is not present. That means D must be present in the candidate key because it is not there in the right hand side. It is we are not getting D in any of the left hand side. Next, E is there, F is there, G is there, H is there. Okay, all are present except D. Okay, that means the attribute D must be present in the candidate key. But from D alone, we cannot get the attributes. We can easily observe, right? From the attribute D, in D closure, we will not get anything. Only we will get D because D is not there in the left hand side of any functional dependency here. That means from here, this we have to understand that we have to add one more attribute with the D to get the given relation. given functional dependent, given the attributes of the relation. Okay. For that, first we will try with D with AD closer. We will find the AD closer because the candidate key always minimum, right? Instead of combining D with CH, I am combining D with A because every time we have to find the minimal, we have to try with the minimum first. If we don't get with the AD closer, BD closer or ED, FD closer, then we will go for the maximum number of attributes. That's why here I am trying to find out the AD closer. From AD closer, what we will get? Initially we will get AD. Okay. From A closer we will get BC. From B closer we are determining CFH. From F closer we are determining EG. From E closer we can determine A, but A is already there. And from CH closer we can determine G. But right now we got all the attributes of the given relation A, B, C, D, E, F, G, H. That means here AD is the candidate key of the given relation. Now, how to find other candidate keys of the relation? For that, we have to see is A is there in right hand side of any given functional dependency? Yes, A is present here, the right hand side of E. Now, what we have to do? That D is always with all the attributes because D is not there in the right hand side. We have to copy the D. Now we have to replace A with E. Now we have to do the closure of AD. In this ED closure also we will get all the attributes. Now we will see in ED closure we will get ED, and in E closure we will get A. E can determine A. Now A can determine BC. Now B can determine CFH. Now F determine EG. E is already here, that's why I am writing only G. A, B, C, D, E, F, G, H. Now itself we got all the attributes of the given relation. Now ED also candidate key. Here AD also candidate key. Now what we have to do? We have to check E is there on the right hand side of any of the given functional dependency. Yes. E is there on the right hand side of F. Now what we have to do? We have to replace E with F. Then D is we have to write as it is because D is not present on the right hand side. Here first, now we have to find the closure of FD. From FD closure what we will get? FD we will get. From F can determine EG. E can determine A. A is determining BC. B is determined F, C, FH, FH. Now we got all the attributes of the given relation A, B, C, D, E, F, G, H. FD is also a candidate key because we from the FD closure we are getting all the attributes of the given relation. Now we have to check is there any other candidate key. For that we have to see F is there on the right hand side of any of the given functional dependencies. Yes, here F is there, right hand side F is there. Which for which attributes right hand side? F is there on the right hand side of B. That means we have to replace F with B. BD closer. We will do BD closer. From BD closer we will get BD, right? B is determining CFH and F is determining EG. E can determine A. Yes, we already got all the functional dependencies. A, B, C, D, E, F, G, H. Yes, BD is also a candidate key of the given relation. Now we will see is there any chance of other candidate keys. Now we have to check B is there on right hand side of any of the given functional dependencies? Yes, B is there. In which, for what right hand side? A. Now we can replace B with A, AD closer. Please observe here, now the it is again repeating. AD closer we already done. We got already. Now whenever we are getting the repetition, now we have to stop the stop finding the candidate keys. Okay, if we do also, we will get the duplicate candidate keys. Again we will get the same candidate keys, not duplicate. Again we will get the same candidate keys. Here AD we are getting again. That's why how many what are the functional dependent what are the candidate keys of this relation? What are the candidate keys of this relation? What are the candidate keys? AD comma ED comma FD comma BD. These are the candidate keys of the this relation. Now what the answer is B, 4. There are 4 candidate keys for this relation. Now we have to find what is the normalization. In which normalization is the given uh, relation is there. For that we will check here. This is F2EG, right? Okay, we got the what are the candidate keys list we got. From the candidate keys list, we can find, right, what are the prime attributes and non-prime attributes. Here the prime attribute means the part of candidate keys. What are the part of candidate keys here? A, D, A, D, E, A, D, E, F, B. A, D, E, F, B. These are the prime attributes. What are non-prime attributes? Which are which are not prime, those are called non-prime attributes. Okay, whichever are not a part of candidate keys, those are called non-prime attributes. A, D, E, F, B. Here, what are the except here? A, D, E, F, B. C, G, H. C, G, H are the non-prime attributes. Yes, am I right? A, D, E, F, B. A, D, E, F, B. C, G, H. Yes, C, G, H are the non-prime attributes. Now we will see. First functional dependency is CH to G. CH is, what is CH here? CH. Yeah, this is a non-prime. Non-prime to G is also non-prime. Non-prime to non-prime. That means this relation is in which normal form? This is in second normal form, right? It cannot be third normal form because non-prime to non-prime is not allowed in 3NF. That's why it is in 2NF. Next, A. What is A? This is the prime attribute. BC. BC. Yeah, C is a non-prime. That means BC is also non-prime. Prime to non-prime means it is partial dependency, right? That means this is in 1NF only. This is not in 2NF. Okay, because B is a prime attribute, but C is non-prime. That means it is a non-prime attribute. Prime to non-prime is partial dependency. Partial dependency is not allowed in second normal form. Again here what is B? B is prime attribute. Again CFH. It is also non-prime. This is also partial dependency, not in 2NF. E. E is also, here E is a prime attribute and A is also prime attribute. We can say that this functional dependency is in 2NF because right hand side prime attribute is allowed in 2NF. We can say that it is in 3NF also. F is non-prime, F is prime attribute and EG. It is also non-prime. That means it is also not in 2NF. This is also not in 2NF. Finally, what we can conclude from this relation, totally this relation is in not in 2NF. Because if any one functional dependency is not following the uh, rules of the second normal form, also total functional dependency becomes that whichever is, yes, here we can say that this functional dependency is 1NF but not in 2NF. Okay, yes, yeah, here see, I clearly write here. Please observe this. Wait 1 minute, I will be coming back. Okay friends, here I clearly explained the above the given relation. This is the finally the given relation is in not 2NF, not in 1NF but not in 2NF, because the relation we found the candidate keys. We got 4 candidate keys: DA, DB, DE, DF. From this we concluded that prime attributes are DA, BEF and non-prime attributes are CGH. Right? Here the first functional dependency CH to G. CH is a non-prime and G is a also non-prime. Then it is in 2NF. Right. Next, A is a prime attributes and B. Yes, here what we did is A to B. I write like this. A to BC. We can write like this, right? Union rule. We can divide this A to B, A to C. If we have confusion, that here what we can observe is B is a prime attribute and C is non-prime. We can say combination of BC is non-prime because one of the attribute is non-prime here. That's why we can say BC is non-prime. But for our clarity, here I wrote A to BC as A to B, A to C. Here A to B is a into NF. A to B is into NF because A is also prime and B is also prime. That means it is in 2NF or 3NF. But A to C is not in 2NF because A is prime attribute and C is non-prime. That's why this is not in 2NF. Again, B to CFH also I have divided this. I write B to CFH like this. B to C, B to F and B to H. I wrote like this. There is no problem, right? Here B is a prime attribute, prime to non-prime. It is also not into NF, not into NF. B, prime attribute to F. Prime to prime means it is in 2NF. BH, B is prime attribute and H is non-prime. This is also not into NF. Like that, it is good to write like this. Whenever any combination of is there in right side, write we can decompose that into separate functional dependencies like this: A to B, A to C. It is good to find the normal form, in which normal form is it is there. Finally, the given relation is in not in 2NF but in 1NF. The answer is, we already saw, right? This is the answer. A is the right answer for this question. Next, this is one more question. Identify the primary key. The given relation is A, B, C, D, E is the given relation, and the given functional dependencies are A to B, C, D to E, B, C to D, and A to D. These are the given functional dependencies. We have to find the what is the key, primary key of the given relation. For that, we have to check the right hand side first. B, C, D, E. B, C, D, E is present, but A is not present in the right hand side. That means A must be there in candidate key. Whichever is not present in right hand side, that attribute will be present in candidate key. That means first we will see the closure of A, because the candidate key should always be minimum, right? In A closure we will get A is determining BC, and BC is determining D, and D is determining E. We got all the attributes of the relation. That means A is a primary key. Rest of anything cannot be a primary key, because if any key is there, that must be combined with A, because right hand side A is not there. The minimum should be primary key, right? The minimum, the primary key of the relation surely will become A. Okay, without A we cannot determine the given relation, because right hand side B, A is not there. We are not getting from A from any of the functional dependencies. That's why whichever is not present in the right hand side, that will be come in the candidate key. Yes friends, here primary key of the relation is A. Now we can okay, now we will check normal form also. What is the normal form of this relation also we will try to find here. The given functional dependencies are A to B, C. A to B, C, how can we write? A to B, A to C. And next dependency is D to E. Next one is B, C to D. If left hand side is more than two attributes, we cannot divide it. Okay, only if right hand side is more than one attribute, we can divide that. A to D is the other functional dependency. Here left hand side is candidate key. That means it is in BCNF. It is also candidate key. It is in BCNF. But here see, what are the prime attributes of this relation? Only A, right? And non-prime attributes? B, C, D, E are the non-prime attributes. Here non-prime to non-prime, because D is non-prime and E is non-prime. Here BC is non-prime, D is also non-prime. A is candidate key, D is non-prime. Finally, this is non-prime to non-prime means this relation is in second normal form. Finally, this relation is in second normal form. Yeah. So the relation is in second normal form. A to B This candidate key to non-prime. Here non-prime to non-prime. That means the relation is in 2NF. Okay friends, now we will see what is relational decomposition. That means we are decomposing the given relation into separate relations. That is called as relational decomposition. When a relation in the relational model is not in appropriate normal form. Okay, if the relation is in not an appropriate normal form, then the decomposition of a relation is required. In a database, it breaks the table into multiple tables. If the relation has no proper decomposition, then it may lead to problems like loss of information. If we cannot decompose the relation in a proper way, maybe some data we can there is a chance of loss of the information. Decomposition is used to eliminate some of the problems of bad design like anomalies, inconsistencies and redundancy. We can uh, remove some of the problems. Okay, what is types of decomposition? Lossless decomposition and lossy decomposition. Sometimes we will get lossless, sometimes we get the lossy decomposition. What is lossless decomposition? If the information is not lost from the relation, that is decomposed. Even though we have decomposed the relation, we are not lost any information. That is called as lossless. The lossless decomposition guarantees that the join of relation will result in same relation as it was decomposed. Lossless means if we combine the decomposed relations, we will get the original relation. The relation is said to be lossless decomposition if natural joins of all the decomposition gives original relation. If we do the natural join of the decomposed relation, we will get the original relation. That is called as lossless decomposition. Here we will see what is lossy and lossless decomposition. There must be for lossy and lossless decomposition, we have to remember these friends. There must be a common attribute in the decomposed table R1 and R2. If we are dividing the given relation R into R1, R2, in R1 and R2 there must be a common attribute, right? What is the need of common attribute? To combine these two relations, right? Common attribute should be there. That common attribute should be candidate key or super key of either R1 and R2 or both for lossless decomposition. When it will be lossless decomposition means we got one attribute R1 intersection R2, we got any one attribute. That attribute should be candidate key of either R1 or R2 or both. Then only the decomposition will become lossless decomposition. If what we have to get, if we do the combination of R1 and R2, we have to get the original relation R. R1 intersection R2 should not become pi. If R1 intersection R2 is not, anything is not there, then that is a lossy decomposition, right? We cannot combine the relations again, then we will not get the original relation. R1 and R2 is lossless if and only if F plus contains either FD. Okay. Yes, in F plus we have to contain all the functional dependencies. See here R1 intersection R2 can determine either R2 minus R1 or R1 minus R2. That means it should be a candidate key for either R2 relation or R1 relation. Okay. Here see one example is there. This is a employee table and this is a department table. employee ID, employee name, employee age, and employee city. Here department ID, employee ID, and employee name. Here how we can find the department ID? We took one common attribute here. R1. Suppose this is the relation R1 and this is the relation R2. If what is R1 intersection R2 here? Employee ID. Then this is a lossless decomposition, right? First of all, it should be R1 intersection R2 it should not equal to pi, not equal to pi, and R1 intersection R2 has to be super key or candidate key of any of the relation, either R1 minus R2 or R1 intersection R2 should be candidate key of R2 minus R1. Then only the decomposition will become lossless decomposition. Otherwise, the relation is in lossy decomposition. Now we will see here, now when these two relations are joined on the common column employee ID, then the resultant relation will look like. Here we are joining these two relations by using these common attributes. See here, first we took the employee ID 22, 33, 46, 52, 60. What is the name of employee ID 22? Danium, and employee age 28, and department name sales, and department ID 827. See here, department ID 827, department name sales. Like this, we are getting all the data. We are not missing any of the data from the above two relations, because the employee ID is the primary key for the employee table. That's why the relation is in lossless joint decomposition. Here the same thing here, it is there. See R1, there must be a R1 intersection R2 has to be super key of R1 minus R2 or R2 minus R1, any one of them. Lossy decomposition means the decomposition of relation R into R1 and R2 is lossy when the join of R1 and R2 does not yield the same relation as R. Suppose if we don't get the original relation by combining R1 and R2, then that is a lossy decomposition. Here we will see one example, then it will be very clear for you. The given relation is RABC is a given relation. But the functional dependency is with functional dependency A to B is decomposed into R1AB, R2BC. Check whether the decomposition is lossy or lossless. First of all, what we have to see, there should be a R1 intersection R2 should not is equal to pi. That means R1 intersection R2B is equal to some common attribute. Here, what is the common attribute of R1 intersection R2? B is the common attribute. Okay. Here see A intersect A comma B, B comma C. What is the intersection? B. We will see first. This is R1 minus R2. R1 minus R2 we are doing. What is R1 minus R2? That means whichever is there common, we have to subtract from R1 to R2. Yes. Now, what is R1 minus R2 means A. Whatever attributes are there in R1, we have to subtract the R2 attributes. Then the remaining in R1 we have to take. Here, what is remaining in R1 after subtracting the attributes from R2? The remaining attribute is A. That means B to A. We have to check the B to A is present in the F plus or not. Is B to A is present in the F plus? A to B. Only A to B is there in the F plus. B to A, we cannot get B to A from A to B, right? So this is not present in F plus. Next we will see R1 intersection R2, R2 minus R1. R1 intersection R2 is B, R2 minus R1 is B, B cancel, C we will get from R2, B to C. So B to C can't determine from the given functional dependency. Here B to C also not there, only A to B is there in the original functional dependency. We cannot get B to C also. None of them contains in the functional dependency, hence the decomposition is lossy. Okay friends, here otherwise we can see like this also. R2 minus R1 minus R2. Is this a key of any of the given relation? B to A is not present, right? B to A is not present in R1 or R2. That's why B is not a super key of the R1 or R2. That's why here this relation is a lossy decomposition, right? We are not getting the original uh, functional dependencies. We will see one more example. Here see the given relation is R A B C D. The functional dependencies are A to B, B to C, and C to D. This is decomposed into R1, R2, R3. We have to combine these three relations, then we have to check if it is lossless decomposition or lossy decomposition. First, what we are doing, R1, R2. What is the intersection of R1 and R2? Anytime we can combine only two relations, right? First, we will combine these two relations. Then, if it is lossless, then we can combine with this relation also. First, what is the intersection of R1 and R2? B. Okay, B. B is the key of R2 minus R1 or R1 minus R2. We will see R1 minus R2. B is the key of this relation. We can easily observe, right? B is the key of this relation. B to C we can determine. From B we can determine C. That's why B is the key of the relation R2. Then we can combine R1 and R2. We already saw, right? The common attribute should be candidate key of any of the two relation R1 and R1 or R2. Here B is the key of the relation R2 because B is determining C, right? Now we can combine these R1 and R2 relation. Now I am giving the name R12. A, B, C is the relation, new relation. Now here we are getting A to B functional dependency and B to C functional dependency we are getting in this relation. Now the other third relation is CD. What is the common attribute from R12 and R3? C is the common attribute. Is C is the key of any of the given relation? Yes, C is the key of the relation R3. Right? C is determining D. That's why we can combine R1, 2, 3. Then the relation will become A, B, C, D. Functional dependencies, what we will get here? A to B, B to C, and C to D we will get here. Okay friends, this is the we got the original original relation and all the functional dependencies from the given relation also we got. A to B we got, B to C we got, and C to D also we got. That's why this this decomposition is a lossless decomposition. We got all the attributes and we got all the original functional dependencies, right? I hope you understand. Then we will go for the next question. Yeah, this is also one more example of lossless or lossless decomposition. Here this is a very big example given. R A B C D E F G H I J is the given relation. The functional dependencies are A B to C, A to D E, B to F, F to G H, and uh, D to I J. Yeah, first relation R1 is A B C, A D E, R3 B F, R4 F G H, R5 D I J. First, we have to combine we have to see the common attribute relations. Here R1 and R2 having common attribute A. That's why we are combining R1 and R2. Yes, A is the common attribute. Is A is the key of any of the relations? Yes. A is the key of R2 relation. A can determine DE. Yes. Here the functional dependency also there. We can combine the relations R1 to A, B, C, D, E. Now this is the relation we got from these R1 and R2. Now we are combining R12 with BF. Now what is the common attribute? B, B. Yes, now B is the key of this relation. R3. Yes, now we can combine R12 and R3. Now we get R123. This is A, B, C, D, E, F. This is the relation we got from the combination of these two. Now we are combining with these two, R123 and R4. What is the common attribute here? Here the common attribute is F. Right? Yes, F is the key of this relation. F is the key of R4 relation. That's why we can combine these two relations. This is R1, 2, 3, 4. Now we are combining Dij with the R5. R1, 2, 3, 4 with Dij. What is the common attribute here? Here D is the common attribute. Now D is the key of the R5. D can determine Ij, right? Dij is there here. Now we can combine this R1, 2, 3, 4 and R5. It will become R1, 2, 3, 4, 5. Now we got the original relation A, B, C, D, E, F, G, H, I, J, and all the original functional dependencies also we got. That's why the decomposition is lossless. I hope you understand this. Please observe once and you will get it. Yeah, one more concept here is dependency preserving. What is dependency preserving? Dependency, it is an important constraint of the database. In the dependency preservation, at least one decomposed table must satisfy every dependency. Whatever the dependencies are there in the original relation, that all dependencies should come from the decomposed relations. That is called as dependency preserving. We will see with example. If a relation R is decomposed into R1 and R2, then the dependencies of R either must be part of R1 or R2. R must be derivable from the combination of functional dependencies of R1 and R2. Suppose if a relation is decomposed into R12, R13. That means all the FDs of R1 should be present in either R1 or R12 or R13, or we have to derive from R1 to R13. Then only it is dependency preserving. Otherwise, it is not dependency preserving. For example, there is a relation RABCD. Functional dependency is A to BC. The relation R is decomposed into R1 ABC, R2 AD, which is dependency preserving. This relation is dependency preserving because the the dependency RABC is a part of the R1 relation, right? We can here A to BC we can add here. That means this is a dependency preserving decomposition relation. Yes, I hope you understand. Now we will see this. Wait 1 minute. Lossless and lossy. Yeah, where are we? Yes, we are here, right? Now we will see dependency preserving decomposition. The decomposition of the relation R F1 F into R1 and R2 with functional dependence Fn and F2 respectively is said to be dependency preserving if and only if F plus is equal to F plus means the dependencies from the given original relation. F plus is equal to F1 union F2 whole plus. If R is a relation R1 R2, these are the functional dependency set. F1 F2 is the functional dependency set for relation R2. Then F1 should subset R equal to F plus and F2 also subset F plus. That means F plus is equivalent to F1 union F2 plus. That means F1 F plus. What is the meaning of this? F plus covers F1 and F plus covers F2, and F plus is equivalent to F1 union F2 plus. We will see with example now. This is a given relation A, B, C. The functional dependencies are A to B, B to C, C to A, and we will solve here. The given relation is A, B, C, and the functional dependencies are A to B, B to C, C to A. The relation is decomposed to R1 AB and R2 BC. What we will get from AB, what functional dependencies we can get here? We can get A to B here. B to C is we can cover here. But C to A we are not covering, right? C to A is not directly, we are not getting C to A. For that, what we have, first of all, from the given relation we have to take the closure of all. From A plus we are getting A, B, C. From A can determine B, B can determine C, C can determine A again. No need. B, B can determine C and C can determine A. Again C plus also C, A, B. That means we can write like this also, right? A to A to B, A to C. From here A to A to B, A to C, and original is B to B, B to C, B to A. And here C to C, C to A, C to B. Now from this here, what can we get again? What are the functional dependencies related to A, B here? A to B we write here, and A to B is covered. B to A also we can write here, right? Because this is relation is having A, B attributes. That means whichever the functional dependencies which are with the combination of A, B, we can write under the relation R1. Okay, that's why anytime while calculating the dependency preserving, we have to find the all the possible closure of all the attributes. Then we have to write like this. Okay, what else coming under the AB? AB is came, BA is came. Then nothing will come A to A we will get here, B to B also we will get here, because A B is there in this, A to A, B to A. Now in BC what we will get, B to B we will get here, C to C we will get, uh, and what else we will get, C to B we will get here. We are not getting C to A, right? We are getting BC also. We are not getting AC and we are not getting CA. Now what we have to do? We have to, uh, by using the R1 union R2, we have to check whether from R1 union R2 are we getting C to A to C or not. If we will get the C to A from the union of R1 and R2, then it is dependency preserving. Otherwise, it is not preserving. Okay, I hope you understand. Whenever the relation is given, first of all, we have to find the uh, closure of everything, the possible closure from the original relation R plus. Next, again, whatever comes under the given relation, we have to write all these here. Now we have to combine the R1 union R2. Here, take the closure of A plus in R1 union R2. I will get A, and A can determine B, B can determine A, and yes, again, B can determine C, C can determine B, B can determine B. That means in A closure we are getting A, B, C. From here we can say that A to B is covering, A to C is also covering. That means A to E is covering, A to C is covering. Next we will see B closure. Yeah, we will see C closure, because we have to get the C to A, right? We are not getting C to A from the original relation. That's why we will see C closure. In C closure, we will get C. C to C can determine B. B can determine A from this R1. Now we are combining R1 and R2. We are watching R1 and R2. We are doing the closure of C. C to A and A to B, again everything will be repeated. In C closure we are getting C, B, A. That means C to C, C to B, C to A also we are covering from the R1 union R2. C to A also covered. B to C initially covered, A to B also covered, C to A also covered. That means we can say that the relation is lossless decomposition, and we have to see is this lossless or lossy decomposition. For that, what we have to do? We have to first see is there any common attribute? Yes, common is B. R1 intersection R2 is B, and B is the key of R2. That's why this is a lossless decomposition also. Lossless decomposition and dependency preserving. Please, I hope you understand, friends. Is it clear now? Everything, the screen is clear now. I hope the lossless and dependency preserving is clear to you. Yeah, whatever I explained, I did here. Please excuse me. The screen is some off screen. It is visible. Uh, I will resolve it. Yes. Yes, this is the what I explained till now. Na? This is my handwritten notes. Okay, this please see this and you will get very clearly. From the given relation we have to see f plus, because in f plus only we will get all dependencies, right? A to B, B to C, C to A. In this, whatever we are getting, we have to see in depth, and whatever are we can write under AB, we have to write under AB. A to B, B to A also we can write here. B to C, C to B also we can write, because this is a relation is having BC attributes. Whatever the functional dependencies contain BC, we have to write under BC, and AB we have to write under AB by using combination of this closure. We are getting C to A also. Initially, by just looking the relation R1 and R2, we are not getting. But by combining these two, we are getting the C to A also. That is meaning that this relation is a lossless decomposition and dependency preserving. Okay, friends, please, this is one more example. Please try to solve it by yourself and you will get it. You have to try, otherwise you will not get the clarity of this concept. Same as previous question. Okay, please try to solve by yourself, and otherwise I will explain in the next class. This is the next example. We will see, it is very easy. This is a given relation M and PQ. M to N and P to Q are the functional dependencies. The relation is decomposed to Mn and R to PQ. The question is asking about the relation is dependency lossless or lossy decomposition, and is this the dependencies are preserving. We can clearly say that from R1 we can cover the M to N dependency, and PQ we can cover P to Q dependency. Here it is a dependency preserving. Just by observing we can say it is a dependency preserving. And uh, is this lossy or lossless decomposition? Is there for that what we have to see? We have to see the intersection of R1 and R2. What is the intersection of R1 and R2 relation? There is nothing is equal to pi. That's why this is a lossy decomposition, because nothing is common means we cannot get the original relation, right? The if for the decomposition is lossless, we should have R1 intersection not is equal to pi. That means R1 intersection should, R2 should contain at least one common attribute. Okay, friends. Here, what is the answer now? It is a dependency preserving but not lossless join. Not lossless. It is not lossless. Okay, not lossless. This is the right answer. Yeah, A is the right answer for this question. Yeah, please try to solve this question by how I write here like this. Please write to try to solve this question. Okay, don't see the answer. Please try to solve this question. Is this what is the answer? Tell me in the comment box. Then I will. Uh, if you don't get, we will see in the next session, friends. Okay. Thank you, friends. If you have any doubt in the normalization and lossless and lossy decomposition and dependency preserving, please ask me. Please put in your comment in the comment box. Please join in the Telegram. I shared the link. Okay. Then we will go for the next topic of the DBMS. I am trying to cover all the important topics from the DBMS. Most of the things we have already covered. Whatever are remaining, I will try to cover in this week. I will complete DBMS. Please try to cooperate and please try to watch the recording. Please, I am giving. Okay, I am helping those who are preparing. If you any one of your friends is preparing, then also you can refer my classes. Okay, thank you friends. Bye. Good evening.